Okay, this is if you had bought one of the recommended textbooks. This is chapter 7 in that book. And it's talking about fault analysis because we have this really useful, powerful tool that we just completed. It's load flow. And so we can calculate all the voltages in our system. Once we have all those voltages, then we can actually go ahead and calculate the currents that would become or that would result of a fault occurring. And why do you need to do that? Because these systems are always energized. They're out exposed to the environments, and stuff just happens over 40, 60, 80-year period. This building is 1960 something. All the electrical is original here. So you're talking 60 years, right? It's not unreasonable to expect to have an electrical failure. So the reason why we have to assume faults in any location is because the fault can occur anywhere on our system. So what we want to be able to do is at least come up with some idea of fault currents and where does the energy come from. Now, we're going to focus mainly on traditional energy systems, primarily because even though there's a lot of renewable energy system, which typically would be called inverter-based, not the hydroelectric ones, but the photovoltaics and the wind, those, well, actually, wind is not, that's not really, it's kind of inverter based, but it's not, depending on the type of turbine you have. So for the most part, though, we're going to be talking about inverter based. And so there's really little to no fault current that those can provide when you compare them to the big synchronous machines. And then at the end, we're going to come up with another generic or standardized approach using our Y bus and using, guess what? Look at that third bullet. Pre-fault voltages. Where do you get pre-fault voltages? From the load flow you just did, right? So you can get the pre-fault voltages plus the Y bus, and you can calculate fault currents for any fault on the system. And you can do it very, very quickly as opposed to having to do it by hand. So that's what we're going to talk about in chapter 7. So where do you get faults? Lightning is one. Not that common to get faults from lightning. Normally you have overhead ground conductors that actually provide some path to ground. You also have lightning arresters that if they get wire gets hit with a piece of lightning by lightning, then you actually have a surge arrestor or a lightning arrestor. That's the same terminology that will shunt any excess voltage as long as it's not overloaded. The other one here is not as common as it used to be, but wires blowing together. If you didn't design the system really well, you literally can have on a 3-phase line wires swinging at different rates. And if they swing and do this, they can actually come into physical contact or get close enough that they'll arc across. The wind farm that I worked on past Dumkeg, that happened after about a year of operation. Crazy, crazy wind. And whoever had designed the distribution circuit or the transmission circuit that went to the towers, they actually didn't have enough tension on the line. So they actually had a contact and they ended up having a trip. By far, the most common one is the third bullet. Animals or plants coming into contact with wires. By far. Because if you don't have a vegetation management program, everybody understands what vegetation management means? It's another way of saying clear out all the brush and trees that are nearby the lines. If you don't clear that out on a regular basis, transmission lines are typically done about every 5 years. That's why if you're driving up and down the interstate, at least in Maine, you'll see these corridors where there's nothing around and just see trees, and all of a sudden you'll see a clear cut. You'll see some bush that are maybe 3 to 4 feet in height, but you don't actually see tall trees growing in there because they actually will spray a pesticide or they'll actually mow the field, the area down about every 5 years to ensure that they don't actually have trees growing up, because eventually over time the trees would go up in the line, potentially causing some problems. Animals, right? Birds can cause problems. More likely going to be a ground-based animal. And what I mean by that, squirrels, raccoons. If you're down south, snakes are notorious for causing that. Because if you think of a snake, right, it has a really long body. And so it has to keep one body on a part of its body on one part. And then as it climbs up, it uses the rest of its body to come into contact with a wire. So snakes are far more common. That's just coming into physical contact with it too. But other animals too are looking for food. So if they see a wire that has insulation, if it's got a type of insulation that they find hasty, I guess, they'll start chewing in the insulation, and then they can cause an arc there. And those tend to be much worse because that's a big arc, and that can cause a lot of problems. Plus, the cable is insulated, which usually means that it's not designed to be close to grounded structures. So if you chewed away the insulation, you can cause a lot of problems. Last one, salt spray or pollution on insulators, way less common. Obviously more common on the coast, but they can happen here. One of the ones that you can say a little bit in Maine is ice, right? If you have a lot of ice buildup, you can actually get some problems there. But generally speaking, the lines are designed with some built-in safety factors that's not an issue. But it's going to happen. I didn't even include another one on there, which is human error. A lot of faults have been caused by human error. A lot used to happen a lot more. And so people would just do work online. They didn't check it was energized. I saw somebody in Texas in the past 6 months that they went to work and they were working on a medium voltage system. They expected it to be de-energized. And instead of confirming that it was de-energized, they actually started working on it and they got severely burned because, you know, they unfortunately they had it de-energized. And so there's things in place now that you can provide some protection for yourself, but it's fairly limited. So human error is another very common one, but hopefully that's getting less and less common with operating procedures and whatnot. So we're going to only focus on 2 types of faults: symmetrical, which means they're all pretty much the same, right? They're not exactly the same, but they're pretty much the same, because in a balanced system, we say all the magnitudes are the same, but offset by 120 degrees. It's the same thing for a symmetrical fault. All the current magnitudes are the same, and the angles are offset by 120, even under fault conditions, okay? But it's basically a symmetrical fault is just adding a really small load, a really big load, depending on your perspective, to pull a lot of current. So symmetrical faults are the easiest to analyze. Anytime you put a load on a system, you could even consider that a fault. Asymmetrical systems is where we're totally changing things up on us, and it's much more complicated to analyze asymmetrical faults, because right now, with a balanced system, we can do single phase analysis, right? One phase has a magnitude and an angle, and the other ones have the same magnitude, but we just phase shift by 120 degrees. Also, we can convert things from phase to phase to neutral. We can no longer do that because in an unbalanced system, our neutral voltages don't necessarily need to be at 0 volts. So they're much more difficult to analyze. But just like in any engineering discipline where you have differential equations for circuits, there's a similar process where we introduce another domain, if you will, where we can make things easier and make the system symmetrical, essentially. Here are other type of asymmetrical faults. This is on a 3-phase system. Not like 80 to 90% of the faults are single line to ground. That's again, the rodent or whatever coming into contact with the phase, they're only going to come into contact with a single phase, right? Or a wire deteriorates over time and you get a fault because that wire comes into contact with ground. Line-to-line faults would be the most common one. Can you think of an example of when a line-to-line fault would occur? Sometimes a tree branch dropping over a couple of the wires, not all 3, but a tree branch could be the issue. Another one, which is kind of sad. Go ahead.
Would this be when the wind is blowing down?
It could be, but again, if it's a properly designed line, that doesn't happen very often. The other one, which is kind of sad, is a bird, right? They're landing on a wire, and if they decide to take off and they flap their wings, and if they go down while they're flapping their wings, potentially, if it's a large enough bird like a raptor, it's possible that it could come into contact with both phases. Possible. And it doesn't actually have to come in contact, it just has to be somewhat close. So line to line is less common, maybe 5%. Double line to ground is you've got a tree that has landed on 2 phases and is still connected to ground. And then the last one, which is the easiest one to analyze, unfortunately, the one that happens the rarest is a balanced 3-phase fault. That means all 3 phases get the same fault. That almost never happens unless somebody screwed something up pretty big time. Let's talk a little bit about lightning, because I think this is interesting. So here's the key thing about lightning. Lightning is a potential difference, right? You have a potential difference between Earth and the clouds, right? And if you actually look at a typical lightning stroke, the lightning actually travels up from ground. I don't know if anybody's ever seen, a camera that could capture it, but the electrons tend to focus on the ground, and the positives tend to focus in the clouds, and so the lightning goes up. But we just call it generally a lightning strike hitting Earth. It actually glows up in the cloud. There's about 30 million lightning strikes per year. Way less common up here in the north. Hardly ever exist in the desert because it's hard to get enough moisture in the air to really build the clouds to do that. So a typical stroke can run about 25,000 amps, which is a pretty high current. But it doesn't last very long. Look at the rise time. It takes about 10 microseconds for it to go from 0 to 25,000 amps, which is almost instantaneous. That's how high the voltage is. It's a very, very rapid change in the current. But it dissipates in 200 microseconds. So even though lightning seems like it has a lot of energy, it really doesn't, right? Because 25,000 amps for something like 10 to 200 milliseconds or microseconds isn't a lot of joules, right? So not a lot. You can also have multiple strikes. And the reason is once you have an ionized path, now all the air molecules are all lined up. So the electrons actually flow a lot easier. So once you get an arc, like if you've ever been to those museums where you walk up and you have the little baton to something and you walk up and you come into contact with it, then you don't see anything. Then you start to pull away and you see a long arc. That's because you've set up an ionized path through there. You can walk up to it and it won't get the conduction. You won't get eventually the lightning, but as you pull it away, you can actually see that you get a pretty big arc. So you got to touch it first, and then you pull it away, and then it'll ionize the air and do it that way. But you can get multiple strokes, and in some cases, you can last up to a full second for the multiple strokes. And then you have this conduction path, which means that ionized air, unless it's particularly windy, is going to stay. So even after the stroke energy has dissipated, you're still going to be getting possibly over 25,000 amps of current. That's why you can see a tree, right, explode if it's been hit by lightning, because 25,000 amps going through something that isn't designed for it, it heats up, that's why they explode. It heats up so quickly, it explodes. And that's the reason too, people, when they see a tree, it usually you see like it's broken in the core. It's not because of the lightning, it's because of the heat that is generated going through the tree. It basically all the water there flashes to steam instantly, and all that pressure is captured in the tree, and it just expands really quickly, and so the tree basically blows apart. Yes, sir.
I heard that there's a quick time to capture the energy from lightning.
Oh, sure, you can try to capture it, but there's not a lot of energy in there, and lightning is very unpredictable. Right? It's not like you can walk outside and say, I'm going to go to this address and there's going to be constant lightning there. It changes. And so is it worth something that might be 2 million volts for 200 microseconds to capture the energy? It's just not really that practical. So it might be a cool idea, but yeah, I don't think anybody's going to try to attempt to capture and do something with the lightning. They do capture the lightning on a transmission line, but then they send it to ground because they don't want it to damage any of the electrical equipment. So they'll pass it to ground. So that's where it's not capturing and doing something with it. It's just basically shunting it off and sending it into a different path. So once we hit lightning, if it's possible with 25,000 amps, you have relaying that's going to sit at each end of the line. And I just say the lines because that's the most likely going to get hit by lightning because it's exposed in the environment. It's unlike it being inside of a building that the equipment is going to be hit by lightning. But 1 to 2 cycles, right? And a cycle is 16.67 milliseconds. The relay is going to say high currents, go ahead and trip. And it's going to try to isolate the line at both ends. Because oftentimes the fault is at the middle of a line. You got to isolate at each end. Otherwise, you can continue to feed it from whichever line stays open. When you actually get the hit, your current goes up, which means your voltage goes down. And then you see some voltages that are dropping. You also see once the breakers are told to trip, it takes a cycle or two for the breakers actually to open and de-energize the line. So now you're taking 4 cycles, maybe 5 cycles. And the standard in industry is it takes usually at least 12 cycles for faults to be detected and for it to be isolated. Anybody have a problem trying to break 10,000 or hundreds of thousands of amps? One thing about a lot of current is you also have some physical, right? Because if you remember from your Emags days, when you have a current flow, you can generate forces. Well, actually pulling apart those connections in your breakers, it takes a lot of work. That's why opening a light switch is no big deal, right? You can flick it on and off. But if you've been in your electrical panel in your house or your dorm room, to flip it open, it actually takes a little bit of real pressure to get that open, right? Because there's a lot more spring tensions in the breakers in your panel than over here. That's just a basic open close, but that's only interrupting 15 amps. Where your breaker, at least for your house, all those breakers are designed to interrupt at least 10,000 amps for fault conditions. So once the line is removed, the voltages go back to near normal. And if it's a lightning hit, and as long as the line is not damaged, one of the best thing you can do is called auto restoration. I want to close those breakers back in if I can and keep the line running. Well, if you can, you don't actually know if the line is damaged until you do a reclose attempt. So one of the ways that you detect that the fault is still there, open the breakers, clear the fault. You hope if the fault is still there, you don't know until you close the system back in. And then if fault current still flows, then you open the breakers again. Sometimes you can do another attempt. I don't know why this term is, but they call it a reclose shot. If you're out in an industry, they call it shot 0, shot 1, shot 2. But they can have up to 4 shots where they'll keep trying to close in, because most faults tend to be very incipient. They in and out like that squirrel that comes in no contact with a wire, that's going to burn away. It's going to clear away. So the squirrel's not going to be there. Most faults, like a down wire, that you shouldn't close back in, but the electrical system can't differentiate between a squirrel or a down line. So they intentionally will have reclose shots to do it. That's why they warn you, right? If you're in a car and you see a wire that's down, stay away from it, because you think it's de-energized because you looked up before and there was an arc and all this stuff and now it's gone. But that doesn't mean in 5 seconds or even less, they won't do a reclose shot and then they'll go ahead and attempt to do that. So that's why you got to use extreme caution because of auto restoration systems. Okay, that's what it is. So auto restoration is a good thing. That means our systems become more reliable. You have high thermal, I squared T, but we also have a lot of physical forces. So you can actually damage things from a mechanical perspective. You can actually have so much force that you can bend or possibly even break some of the equipment inside those systems. So what we're going to do is determine what the magnitudes of the current can be during this fault. That's what we're going to do today. Then we're going to pick devices that can interrupt those expected levels of current. And not only interrupt, but sometimes they just need to survive the fault current. So they're not intended to interrupt that current, because what we'll learn is the fault current over time decays away to a certain period or a certain period. So if it's really, a lot of fault current initially, the breaker can't interrupt that. It can only withstand that. Then you have to be able to interrupt that after a few cycles. And that's what we're talking about here. All right. So let's do RL circuit. Why an RL circuit? Because that's what the transmission line is, right? It's a resistor and inductor. The transformer is a resistor and inductor. The generator is a resistor inductor. You do have some capacitance to ground on lines, but for the vast majority of cases, they're going to be primarily inductive and resistive. Yes, sir.
What do you mean by the breaker can't interrupt the fault?
Because if I have a breaker that's rated for 100,000 amps, that breaker might initially, for a very short period of time, see 160,000 amps going through it. If I tried to open that breaker up when there's 160,000 amps, it's too much force. And so while it's pulling open, the force is trying to keep it closed. And so the contacts actually bend, and then you can't open it. There are devices like all you know what a motor air compressor is, or an HVAC system. Those things are cycling on and off all the time, right? So they have what's called a contactor that open close, just like our switch, open close, open close, open close, maybe millions of times. But that's just opening and closing a small amount of current. But if a fault occurs, that contactor tries to open during a fault, it's going to damage the contactor. It can't do it. So what you do is you actually put a fuse in series with the contactor, and the fuse will interrupt the fault current, and the contactor can stay closed. So there are devices that are specifically designed, like they're called motor starters, that they have a contactor in series with a fuse, And that's how they actually trip. That's how they remove the faults or isolate faults. They let the fuse take it out. So here's our RL circuit. We can see a power supply, and we got to do things in the time domain because in the case of a fault, we actually have some time varying quantities. So let's go back to the time domain just for a little while. So if you remember back when we looked at sinusoidally varying waveforms, we had a generic equation written like that. Then we have a resistor and inductor, and we don't necessarily care. Before the switch is closed, right before a fault occurs, we've got no current going to the fault. We may have current going to the load, but generally speaking, fault current is so much greater than load current, then we can neglect any load current. Because if you're running something that has 1,000 amps of load and your fault current is 80,000 amps, the calculation to include that load current really doesn't throw you off all that much. So we usually neglect any of the load values. When we close the switch, we'll have two parts. Remember from 209 or 324, I think, whenever you have an inductor, you can have some initial charge. And in this case, you've got a steady state value, which is from the power supply, and the transient value, which is as a result of the inductor, whatever initial charge is on the magnetic field associated with the inductor. That's the natural response. So we want to go ahead and calculate our steady state AC component because everything we're doing is in AC. So all I'm going to do is write a time domain equation, which is going to be my voltage divided by my impedance. Now, you can say, how is this a time domain? Well, my value of Z has omega L, right, which is the steady state value. But all I need to do is this is the magnitude of Z, and this is going to be the corresponding phase shift that we see from the impedance that we see or that we get. So all we need to do is go V divided by Z, which is going to be equal to whatever the voltage is, right? The magnitude of the voltage at an angle of the voltage divided by Z magnitude at an angle of theta Z. That's where the theta Z comes from. If you're just doing complex math and you're just incorporating it into the sine wave. So we know how to get magnitude and we can get the magnitude and the angle associated with Z. Remember, it's a right triangle. So that's just SOHCAHTOA. And our AC value, our steady state value, would just be equal to V divided by Z. Now we've got to get our natural response term, which is going to be a DC part, because do you all remember from 209 to 324, this is just a first order circuit, right? So a first order circuit with an R and an L has a solution that looks like C e to the minus T over tau. That might even be back from physics too, right? Some of you might have learned about time constants in second semester physics. So that's C e to the minus T over tau. My time constant for a resistive inductive circuit is L over R. So now we're going to go ahead and add all that up and solve for our initial condition. Why did I say I of 0 equals 0? See if we got our thinking caps on. Why does I of 0 equal 0 when we energize this circuit? Yes, sir. No, the switch is closed at time t equals 0. Yes, sir.
Because the current through the inductor can't change instantaneously, so because it was 0 at T0 minus when the switch was open, when the switch is closed, it has to stay.
That's exactly right. You can't have an instantaneous change in current, can you? So if there's no current flow through the inductor before the switch, how much current will flow after, just after the switch closes? Nothing. So I'm trying to solve for my initial condition components, my C's here, right? So I set that equal to 0, and I can solve for what that DC offset needs to be, what that inductor is attempting to do so that that current won't instantaneously change. It either will try to store massive amounts of current, or try to dump it out, depending on the condition. So you can see my value of C1, it's just a parameter, but it's heavily dependent on where you are in the sine wave. That alpha term is where you are in the sine wave. Are you at 30 degrees, 45 degrees, et cetera, et cetera, et cetera. So you can see, when will the sine of alpha minus theta of z be at its greatest? Any ideas?
When the two of them are 90 degrees apart.
Right. When they are 90 degrees apart, you end up with the peak value. So the peak value becomes square root of 2 v over z. That's the C1 component. And the hard part is we have to assume the worst case scenario because we don't know when we're going to close. Even though we only have 2 times a cycle where that's going to occur, we got to make sure our electrical systems operate safely so they can take our system out. So we're going to assume worst case, our C1 coefficient is going to be square root of 2 v over z. So now we'll add our AC and our DC parts together and we get the equation on the bottom. So you can see we have the forced response and the natural response. And you know it's the natural response because it's a decaying exponential. It isn't periodic, so you can't do an RMS value, right? We can't do the sum of the squares and do all that stuff. That doesn't really work for us. But we're going to approximate it by taking the sum of the AC part squared and the DC part squared, so we can end up with a more simplified equation. We have an IAC, which is the RMS value, multiplied by 1 plus 2 e to the minus t over tau. And then the worst case, the absolute worst case result is whatever your AC current value, whatever your symmetrical current value is going to be, your AC plus your DC value will be square root of 3 times that. That's what the actual worst case scenario will be. And breakers are designed to handle this. They actually have a symmetrical rating. Let's say it's rated for 100,000 amp, but then they have an asymmetrical rating, including that DC offset, which includes this square root of 3 multiplier. All right. So that's built into the manufacturer's design. They're not going to only interrupt the symmetrical value. They got to be able to interrupt over and above because that DC offset moves your sine wave up. Oh, yes, sir.
What is this? What was the example?
Because what is the worst case that I get here? E to the minus t over 2, e to the minus 2t over tau. That's when that equals 1. The maximum you're ever going to see is 1 plus 2, right? Can never be e to whatever, can never be greater than 1 in this case because it's a negative number. So that's where you get the square root of 3. 1 plus 2 equals 3. So that's how you can find that asymmetrical value. Take your symmetrical fault current and multiply that by the square root of 3. And now you know the absolute worst case asymmetrical value. Absolute 100% worst case. And again, if you go buy a breaker, that's what it's rated for. So you'll buy a breaker on a symmetrical current rating, but internal to that, you have this capability that's above and beyond because of the DC offset. So now we're going to extend this a little bit to see where the energy comes from. And this is a picture of a machine, right? See, it's a rotating machine. You've got a bunch of wires here. Hopefully that's legible. And those are windings, right? Do you see any more windings on here? I didn't really do a good job of highlighting that one. A winding is a loop of wire, right? That goes back and forth around the rotor of the mechanical system that you have. Do you have any more in here? Yes, sir.
Doesn't it make one really big one around the entire, like, shaft?
No, because a shaft is electrically insulated, so generally not. There's one more winding, at least one more winding staring at you. It's really bright and shiny. Here. See that copper bar? You see how it's connected to these? This is hard to see, but you can see these are welded in place on that copper bar. These go all the way through. And on the other side has exactly the same configuration. So this here is usually denoted the field winding. And this winding right here is either the damper or our mortar saw. I don't know if I have that spelled perfectly correctly, but those are the mortar saw windings. And the field windings are necessary to set up the magnetic field so that you get the voltage that you want. The damper windings are there to smooth out the operation. They help, deal with transients or very fast or rapidly moving changes. But what I see is I have an inductor here and an inductor here, which means I've got a couple devices that can store energy. And hopefully what you see, I've got pretty small wire here with a lot of turns, and I've got pretty big wire here. I got a bar with not a lot of turns. So you actually have a time constant with the field and a time constant with the damper. Each of those systems can dissipate energy at different rates. So because of that, let's modify our synchronous generator representation, which has an ideal voltage source in series with an inductor. And notice I don't have the resistor in there because, again, we're going to ignore it because it's pretty small. And I'm no longer going to call that XD. Remember back when we looked at our parameters? Actually, I can do it here. But remember Dolby, the real world per unit example? And we looked at the D8, that was the Dolby 8 generator. XD. You see XD there? That's the direct access reactance. And notice there's 3 XDs. XD, XD prime, and XD double prime. If you had to make a wager as to which generator or which condition would put out more fault current, would it be when you have XD double prime, XD single prime, or XD without a prime?
XD double prime.
Why?
Because it's a smaller impedance, so the fault current would be higher.
Yeah, 1 divided by 0.18 is going to be a heck of a lot bigger than 1 divided by 0.75, right? So under XD double prime conditions is the most amount of current. XD prime is the next case, going to be a little bit less current because you can see the number's gone up from 0.18 to 0.26. And then XD without a prime is when that machine, that's what it can produce. I say indefinitely, but there's no there's no decaying exponential there. At that point, what you have is the machine is putting out way more current than it's designed to handle, but that's what it can do continuously as long as you could keep it cool. So we do the same thing here, and our XD is going to vary. XD double prime, XD single prime, and XD. And we use the direct access. If you want to learn more about direct and quadrature access, because if you look over here, there is an XQ. That has to do with, it's called a rotating reference frame. And if you're trying to look at things from a transient analysis, it's better to have the XDs and the XQs as shown. But for what we're doing, XD is all we need. So we can use our direct access impedances. And for what it's worth, XD double prime stands for sub-transient. So start to think about the term transient, what that means. So that's sub-transient. XD single prime is the transient value, and XD is the steady state value. So remember we talked about the times when the amount of current is being delivered. XD double prime is sub-transient, so very fast. XD single prime is not quite as fast. And then lastly, XD is what it can deliver as long as the machine doesn't burn up. And that's where it's spelled out. So way back when we did the real world per unit, I said, the reason why I'm giving you this data sheet is because it has relevant and pertinent information for later courses of study. Here we are. When we're doing fault analysis, this is when we actually need the material. So how do we figure out what the actual output current is going to be? This one, if we want to go back and we want to assume we don't know in the closing, we're going to close this in. So what time we're in the sine wave, that's what the omega t represent. The alpha is the phase shift between the voltage and the current. And then the pi over 2 is, where do we get the pi over 2? We only have an inductor in our circuit, right? What kind of a phase shift do we get with an inductor? 90 degrees, right? So that pi over 2 is because the inductor, the generator, we're just representing it as purely inductive machine. So the pi over 2 comes from the fact that you have JXL. So here's the equation. And as you walk through time, as indicated by the time constant, you can see what the current is. And because we want this to be one equation, we have to kind of write an extended equation. We have 1 over XD, which is the steady state value. So if we're after 5 time constants, that's the only one that's left. Then we go 1 over XD prime minus 1 over XD. So if we're under a short time period or shorter time period, then the 1 over XD prime and the minus 1 over XD come into play. So that would cancel out the steady state value, and you just get the fault current contribution from the transient value. If it's even shorter than that, then we'll cancel out the transient current contribution and just do the subtransient. So we're not adding all 3 together. We only have the subtransient for 3 to 5 cycles. Then we move to transient for 3 to 5 cycles. And then from there on, we move to steady state. And you can see some typical time constants. Usually in about 2 cycles is the subtransient time constant. So you can see 6 to 10 cycles, your subtransient term dies away. And then your transient time constant is around a second. So from 3 to 5 seconds of operation is when your transient value goes away. And typically, then you're left with steady state. When I talked about what do breakers need to interrupt, it's very difficult to have them interrupt during the direct access of the subtransient time, because the relays just don't respond fast enough. The breakers don't respond. So they don't really need to interrupt that level of current. What they typically need to be able to interrupt is the transient time, okay? So if they can interrupt the transient time because that's more current, then doing the steady state is no problem. But more often than not, your breakers have to be able to, and your machine has to be able to withstand the amount of current that's available during the subtransient time and interrupt during the transient time. And that's getting more and more challenging, because what we're learning with the power system is if we can isolate faults faster, not only do we have less equipment damage, but we actually have a more reliable system. Because if you keep a fault on too long, you can actually trip off other parts of the system because everybody gets out of sync. Well, if you go with 1 cycle breakers, normally the standard is like 3 to 5 cycle, but if you get 1 cycle breakers and very, very fast acting protection schemes, you can trip much faster, and now you're starting to encroach into perhaps the subtransient time. So now the breakers have to be much heavier duty. But again, there's advantages to that because you have a more stable system. And then our max DC offset, you can see this is worst case is we're going to have our EA double prime over XD prime. Where does the EA double prime come from? You may be asking. Well, if I go over here, do you remember how we did our calculations and we always assumed that this terminal voltage was 1 per unit? We calculate the voltage drop through here, and then we calculate what the actual power supply could be. So you can do that for the subtransient time as well as the transient time. So your internally generated voltages can vary. It just depends on what transient impedance or what impedance you're going to be using to represent the generator. So that's where I calculate EA. It's just a KVL loop. And here are typical waveforms for a 3-phase fault. You can see on phase A, we close right at the sine wave being at 0. So remember what the inductor does. Hey, it was 0 right before the switch transition occurred. It's 0 just after. So the inductor doesn't do anything. No DC offset in the first one, do you? You just see a sine wave that's exponentially decaying because of the transient time. It's not because it's DC, it's just because the time has elapsed. So there's no DC offset in the first one. In C, it closes at the exact wrong time, but in the negative direction, and you can look at how much negative current. And again, it doesn't matter if it's negative or positive current, it's just the magnitude of current. You can see how far down that goes, way more than phase A. Similarly for phase B, but in the opposite direction. So because you can have a 3-phase fault, and you can see one phase doesn't have much of an offset, but the other two are max, Now you have to be able to size the breaker to be able to interrupt all of these three of these conditions. So that's why you've got to assume the worst case. Unless you're going what are called independent pole operated breakers, and you are forcing the breaker to open during a zero crossing. But I've only done one independent pole operating breaker in my life, and they're very expensive and you don't see them very often. But you can see, hopefully, the DC offset and the decaying exponential not because of the inductor effect on the contribution of energy, but because of the DC offset to make sure that that current doesn't instantaneously change. Here's an image, kind of more zoomed in, if you will, and you can see the different current magnitudes. And we're going to simplify, instead of calling this EA double prime, EA prime, and EA zero, we're just going to either call it EA prime or EA. We're only going to calculate one generator pre-fault voltage and assume that that pre-fault voltage stays the same under all conditions. The only thing that's going to change is the value of X. So this numerator term is a constant. The only term that you'll see is the XD term that is in the denominator. So that's where you get the higher values. And again, this shows the subtransient transient, but it doesn't actually show any DC offset because of the inductor. Because again, you'd actually have to have that information. We've already included it with that sort of that peak value. So let's take a look at example 500 MVA generator, which is a pretty darn big generator. Most generators are less than 100 MVA. But 500 MVA, 20 kV, three-phase machine has an internal voltage. That's another way to say EA, right? Internal voltage is EA of 1.05 per unit. We're going to assume a three-phase fault occurs at the generator terminals, not somewhere out on the line. Why do we have it at the generator terminals and not somewhere out on the line? Yeah, I'd have to worry about the line impedance, right? So if the fault occurs 50 miles away from the generator, I have all this impedance between there, so my fault current's going to be a lot less. I'm trying to calculate worst case conditions, so I'm going to include it right at the terminal. And most of the projects, not all the projects, but most of the projects I've seen, the generator has what we call a generator circuit breaker, a breaker dedicated to isolating and protecting the generator. And so essentially there's almost no impedance to the breaker because they usually tend to be very close. So I want to determine the fault current. And it says here, it says after 3 cycles, the breaker opens. So I want to see what the fault current is at 3 cycles, how much fault current that breaker needs to interrupt. So I've given you the subtransient, transient, and steady state impedances all in per unit, just like we did here, right? Steady state, transient, and subtransient impedances all there. And this one, I don't even bother showing you saturated or unsaturated. We won't spend too much time talking about that. That has to just do with the non-linearity of electric machines. But we do have saturated and unsaturated values. If you want to learn more about that, the predecessor to this class is EET422, but I don't know, maybe the EETs can talk better about it. The EET422 is a class more focused on machines. We do also cover AC circuit analysis, but we spend more time looking in the machinery. So we've spent a little more time doing transformers, motors, and generators. We have our time constants here. We have TD prime and TD double prime. There is no TD, right? Because that's the steady state value. We also have an armature time constant of 0.2 seconds to help us figure out what our DC offset's going to be. So now we just plug it in to our equation, right? That's the one we developed. And you can see all the parameters specified there. Now we're going to plug in our T value. So, I'm sorry. So this is going to be what the current is going to be, worst case, right? It is 7 per unit times the normal current. Normal current would be what it normally can provide. So if it's delivering 7 times the current, that generator is not going to last very long. If it's a 500 MVA generator, then I can go ahead and calculate what the base current needs to be, 14,000 amps. And then the initial current for a fault occurring is going to be just over 100,000 amps. Now I add in the DC component, again, just after the fault occurs. And I've got to add to that my 143, and then I do the RMS value. and I end up with 175,000 amps of fault current just after the device closes. If you want to know what happens in 3 cycles, you say T equals 3 divided by 60, right? Because each cycle is 1/60th of a second. So 3 divided by 60, or 1/20th, you plug that in there, and you can actually calculate what the current needs to be. Does anybody want to see what that current is after 3 cycles? It says here, assume a 3-phase fault. Breaker operates after 3 cycles. You want to see what the current actually has to interrupt. Okay. So our AC current, we'll just put that in MATLAB. So I'll say IAC is going to be equal to, whoops. So 1.05 times, and this is going to take a little bit of, so I got to have my bracket. So this is 1 divided by 1.1 plus 1 divided by 0.24 minus 1 divided by 1.1. And that's e to the minus negative 120. Oh. Negative 120 divided by tau, which is 2, plus my next one. I'm just going to copy this one over because it's almost the same format. I just have to change the numbers around a little bit. So this is going to be 1.24. This is going to be 0.15. And this time constant changes to 0.035. Did I make a mistake?
Is MATLAB okay with no leading 0?
Yeah, it's fine. Did I forget to put the parentheses here? All right. What, it doesn't support the use of equal. Oh, I know why. I don't have a closed bracket. Sorry about that. I need to close the bracket here, I believe. So after 3 cycles, just the AC current alone, not even the DC offset, is almost 5 per unit. So that'd be 5 times the 14,000 amps. So this breaker has to interrupt. The AC part of it is 90. I'd have to do the same thing over here. I can do the delay for the DC one to see what the symmetrical value is. So I'd do the 101 times the square root of 2. And I could add it that way, but I'm really more focused on the AC. So you're pulling about 90,000 amps is what you need to interrupt after 3 cycles. If you move that to 2 cycles, you got to redo your work. And instead of 1/20, this becomes 1/30, right? So this is going to be even more current. And then if you're going to do 1/60, which means it's a 1 cycle breaker, now you're at 6 per unit, right? Now you're talking over 100,000 amps. No, 84,000 amps. So got a lot of current. No, 6 times 5 times 14, that's 70. So this goes up to 84,000 amps. So the faster the breaker, not only is it a faster operating breaker with more mechanical ohm, but it also has to be able to interrupt more fault current. So 1 cycle breakers are a lot more expensive. Don't see a lot of them. I actually have never seen them, but they are coming around. So here's the work. We have a 111 and we add the 2 up. We get 132K with the RMS. That's adding the DC value. Questions on here, because this is the majority of the fault current contribution is from synchronous machines. Inverter-based generators don't have this capability. Why? They don't have any energy storage, right? You don't have inductors that can store energy. So when you have a fault, Usually they can only put out 1.1 to 1.2 per unit current. So if you actually get a fault on a system that has an inverter, you might not even know that there's a fault out there. Because 1.1 or 1.2 per unit multiplier of the full load amps is usually less than the protective device settings. So that's the worst problem about inverters, is there's just not enough fault current. So you can have a fault on a system and the inverter will crank out 1.1 or 1.2 per unit. The voltage will go in the toilet, but it'll sit there and feed the fault all day, and then the fault won't get cleared. So way more challenges with inverter-based generation when you have a machine that can put out 7 times the full load amps. So fault current is a good thing when you're trying to detect it. It's a bad thing all the other times, but for detection purposes, it needs to be there. So your systems actually have to have sufficient fault current to help you locate faults. Yes, sir.
Is it possible to have an half cycle breaker?
Yeah. They actually don't go breakers. The fastest device that I know of is quarter cycle, and those are called current limiting fuses. So a current limiting fuse is just a fuse, but inside the fuse, you have it. So it's in a shell. It's usually like either a plastic or a glass, like an insulated shell, and you can't see it. But then they have the metallic element that actually carries current, and it's the size and dimensions you need. All around the fuse is sand. So when the fuse is running at too high of a temperature, too high a current, it generates a temperature. What happens to sand when it gets hot? Turns to glass. So now you've got glass that's leaning on the stuff that's melting, and it makes it impossible for current to conduct. And the glass forms very quickly, like I said, less than a quarter of a cycle, which is less than 4.5 milliseconds. And so the fault current gets shunted very quickly. So the fastest devices to isolate current today still is a quarter cycle, and those are current limiting fuses. But I don't know of any breaker that can do it in half a cycle. The relays can't operate any faster than 1 or 2 cycles, so you still have to put that in anyway. But if you go to IEEE, the fastest that they recommend is 12 cycles, which includes 3 to 5 cycles for breaker operation time. They just say it takes 12 cycles. So your system's got to be able to handle or withstand all that current for that period of time. But it's a good question. You don't see a lot of fuses. Well, let me back up. You see millions and millions of fuses, but you don't see them in important applications. Why is that? What did we say at the beginning of class is a really important feature of our power system? Auto restoration. Are fuses auto restorable? No. They do have resettable fuses, but they're not that common. Usually once a fuse burns, you got to go out and manually reset it. So there's no auto part for restoration. It's called manual restoration. So if a fuse that's going down to a line that goes to your house, if that burns out, you're going to be out of power for as long as it takes for a crew to get out there. If you're a breaker or a recloser and you're out on the line and the system is getting restored, they'll try to reclose in and get you on. And usually those who are closest to reclosers will connect very, very quickly. So there are actual reclosing schemes that are actually called fuse savers. They actually will trip faster than the fuse. So even though the fuse is closer to where the fault is, and it would make sense to let the fuse clear the fault, what they'll do is they'll actually have the recloser operate, say, hey, remove the fault before the fuse actually melts, because those faults are temporary in nature. So then they'll close down. So that's a good thing because you save those customers from being out of power for a long period of time. The downside with it, though, is that when you had a trip, a reclose operation, you had 1,000 homes taken out of service where you could have had maybe 10. So there's more annoyance factor, right? When you have those 1,000 houses versus 10. So it's a balance thing, right? So do you fuse save and take out 1,000 customers for maybe 5 seconds? Because then the lights flicker, that's not too bad. Or do you let the fuse take it out and those customers may be out of power for days? I had a problem at my house. This is a couple of years ago. I had no power. I lived right in town Bangor in a fairly populated area. When I say fairly populated, this is Bangor, Maine, right? I didn't have power for 6 days. That's not expected when you live right in town. But there was a down line, and the line was the fuse, basically. They didn't care about the line. So if it was too much current, they'd let the line melt. They didn't care. So, any questions while we're here, the banging? Can you hear the banging in TV land?
Not at all.
Can you hear it here in live TV land? It's pretty loud.
Yeah, appreciate it.
Yeah, some technical difficulties here, so. All right, so for next class on Thursday, what are we gonna be doing? Exam 2 review, because a week from yesterday will be your second exam. And remember, your homework, pretty good indication of understanding the concepts for load flows. I'm not gonna expect you to do a 3-bus load flow with 4 equations and 4 unknowns, right? Because how many people got number 2 right on the homework?
We don't know.
Did it converge? Did you get reasonable numbers around 0 degrees and around 1 per unit voltage? You gotta speak up because all I hear is banging.
Yeah. But
Okay, so you might have got it. So how long did it take you to get all that working? Few hours, maybe? More than what you could do during a test. And it doesn't necessarily demonstrate knowledge. It's more about setting up the process, right? And doing that. So I'm more interested in you doing what the calculations are, understanding the calculation or setting up the equations and actually doing the calculations. Because he said it took him 2 hours to do 1 iteration on a calculator. That's not what I intended to do on a test. Because how frustrating it is, you spent 2 hours and you put a negative sign instead of a positive sign. Now you gotta do another 2 hours. Like, yeah, he was telling me he's had a sign instead of a cosine. He's like, oh, and how much time did you spend looking at it saying, there's no way this is wrong? It's frustrating, yeah. That's why I offered that service, which is if you wanted to check your Jacobian. All right, I'm gonna definitely end it because it's getting some banging. So have a great day, everyone. See you on Thursday. Make sure you come ready with questions. Take care.